one, what is the electric field at, let's say call this A, at A, what is the electric field? So the way we go ahead with it is this. First, draw a Gaussian surface. So if you draw a Gaussian surface here, the Gaussian surface encloses a charge Q. So the electric field at A is going to be equal to KQ by R square, where R is a number which is less than, suppose this is some B, less than B, the radius of the shell. Now this is a shell. This is a shell. Okay, a conducting shell. So now here the point to understand is that there is a charge 2Q, thus does not affect the electric field. 3Q also does not affect the electric field. Okay, the electric field inside the shell is influenced only by the charge which is there inside. Now, why? Because this shell shields this point A from 3Q. The shell provides the electrostatic shielding whatever is that, suppose we call that A to point A. So this outer charge here will not influence. Then next question I am asking you is, what is the net force on the charge placed at the center? So the net force is 0. Why is it 0? Because there is no external field there. Only if there is an external field there can be a force. So there is no external field there, so there is no net force. Next question, what is the force on 3Q? Now it's very simple. So first I draw Gaussian surface. The total charge inside is 2Q and Q, 3Q. So it is the electric field there at 3Q is K 3Q by A squared, where this distance from here to here is A. This is the electric field. Electric field is equal to K 3Q by A squared. Now at that point you are putting a charge 3Q. So it becomes K 9Q squared by A squared. So that is 9K Q squared by A squared is the force acting on 3Q. Okay. So what we are trying to say is Q is shielded by 3Q. But 3Q is not shielded from Q. Okay. So that is basically what we are trying to explain. The next question where students asked me a doubt is this. There is a sphere here. I am drawing another cavity here. So suppose this is, okay, let's take up a question. Question, a sphere is uniformly charged. Let's call this volume charge. Volume charge density is rho. Now, suppose there are 2 points. Suppose this radius here is, okay, a sphere is uniformly charged. A cavity is dug. The radius is, let's call this R by 2. The question is, suppose you identify a point here A and you identify a point here B. What is the electric field at A divided by the electric field at B? So this is the question. Yeah. So if I have to answer this question, let me try to work it out. See, First, let me want to find out the electric field at A. A is basically the center of the sphere. Technically, the electric field at the center of sphere would have been 0. Remember the graph? It goes like this, and then it goes like this. So if I draw a small Gaussian surface, the total charge inside will be 0. So it will go like this. It will be 0. But now you are removing this this cavity here. So if you are removing this cavity here, the electric field there would be the original electric field minus the electric field due to the cavity. So because of this, what will be the electric field here? So because of this, that's a spherical cavity. So spherical cavity on its surface would have, again, if I apply Gauss law, E dot dA is equal to Q by epsilon naught. So E into 4 pi R by, okay, R squared is equal to rho into 4 by 3 pi R cubed by epsilon naught. This 4 pi gets cancelled, R squared gets cancelled. So the electric field is simply rho R by 3 epsilon naught. Here R is how much? R by 2. So it becomes rho R by 6 epsilon naught. So the electric field at A will be minus rho R by 6 epsilon naught. See, if everything was solid, the electric field here would have been 0. But now you are removing this. When you are removing this, the electric field at this particular point, I'm applying Gauss law and then I hold it. Yeah. Now the electric field at this point. If everything was there, the electric field at B would have been equal to rho R by 3 epsilon naught. Now I want to know what is the electric field due to this at this point. So at all external points, the charge would have behaved as if it is located at the center. So that will give you minus k cube by r squared. So that will give you k, q is how much? Rho into 4 by 3 pi r cube by 8 divided by r squared. So capital R squared. So not capital R squared, it will be from the center here. So it will become 9r squared. This is 3r. Now it will become 3r by 2. So it will become 9r squared by 4. So 4 here. So now when I simplify this, let me see. So this 4. So wait, r squared here, this goes. 4 will go 2 times. 2 will go 2 times. So it becomes minus 2 by 27. 2 by 27. This k is 1 by 4 pi epsilon naught because we have written it like that. So we will write this as 1 by 4 pi epsilon naught. So here this pi again goes off. Pi gets cancelled. 2 will get here 2 times. So it becomes 1 by 54. So it is 1 by 54. 1 by 54. K is removed. Rho R by epsilon naught. Now this part you may have a doubt again. So let me take you to a new page and then do it. See, it was like this, right? I'm talking about the electric field here. Had this all been there, full solid been there, the electric field here would have been kq by r squared. So k is 1 by 4 pi epsilon naught. Q is 4 by 3 pi r cubed by r squared. That is r squared. So this much. So this 4 pi would have been got cancelled. R squared would have got cancelled, and it would become rho r by 3 epsilon. This is what would have been had this full thing been solid. But now when you are removing this, so the influence of this at this point will go away. So the electric field there would be this rho r by 3 epsilon naught minus the electric field due to this here. What is the electric field due to this here? So this is a charge at all points outside. The charge behaves as if it is located at the center. So this distance here is 3r by 2. So 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught k q. Q is how much? 4 by 3 pi r cubed by 8 into rho by r squared. R squared is 9r squared by 4. So the 4 goes up. Yeah. So now this 4 pi here gets cancelled. 4 will get cancelled here 2 times. R squared will get cancelled here. So it becomes rho r by 3 epsilon naught minus minus 9 into 2. 9 into 2 is what? 18. 18 into 3 is 54. So 1 by 54 rho r by epsilon. So this, when I do this thing, the LCM is 54 itself. So here it will become 54 means what? 18. So it will become 17. So 17 rho r by 54 epsilon naught. So they asked you EA by EB. EA by EB is equal to, EB is 17 rho r by 54 epsilon naught. EA we have already found out. EA we have found out was rho r by 6 epsilon naught. So that is rho r by 6 epsilon naught. So this rho r got cancelled, epsilon got cancelled, 54 goes up. 54 by 6 into 17. So 6 will go 9 times, so it becomes 9 by 17. So EA by EB is equal to 9 by 17. I hope you understand the application, I mean how we applied this. Okay. So for all this to happen, this must be an insulator. Only if it's an insulator, it would work out. So I'll summarize again. So there was a sphere. They dug a sphere through it, which has a radius r by 2. They identified the center of the sphere. They identified this. They so took A, they took B, and they asked us to find out the electric field. So the way we found out the electric field, E at A is equal to E original. That is assuming the sphere was full minus E cavity. If the sphere was full, the electric field at A would have been 0. Now we found out the electric field due to this by using Gauss law. Then we found out that that was equal to rho r by 6 epsilon naught. If you want me to do that again, I don't mind doing that again. So basically it is rho r by 3 epsilon naught, r is r by 2. So over. Then the electric field at B was E original minus the electric field due to cavity at B. Now E original was the original electric field, that is rho r by 3 epsilon naught minus the electric field due to cavity at B. This time this distance here is 3r by 2. And because it is outside, I have to use only kq squared by r squared. Kq by r squared. So I got that as rho r by 54 epsilon naught. If you want to understand this better, I'll do it again with a different color so that you get it. So it is k 1 by 4 pi epsilon naught q. Q is 4 pi r cubed by 8 into rho into 4 by 3 pi r cubed into, see, this is 1 by 4 pi epsilon naught q, 1 by 4 pi epsilon naught q by r squared. R squared is 9 squared by 4. So 4 goes up by 9 squared. So I think I made some mistake. Not 9 squared, 3 squared. 3 squared is 9 by 4. So now this 4 pi here, this 4 pi here gets cancelled. 4 gets cancelled here to give it 2 times. So 9 into 6 is 54. So 54, this rho r squared will be there here. So r squared r will get cancelled. Rho r by 54 epsilon. So I found this out, and I found out the ratio. So think about this for some time. How I worked it out. Take some time, digest the question, and then work. The question was that consider a sphere of some radius r, which has a uniform volume charge density. So whenever any sphere has uniform volume charge density, we understand that it has to be a insulating sphere. So we did that. Then inside that there is a cavity of r by 2. So we dug a cavity r by 2, and then we found out. Same thing I have done here. This explains a little bit better. Okay. Now I'll go back to the question that I had discussed the other day. That there is a sphere here and there is a spherical cavity here. Okay. If I need to know what is the electric field at the spherical cavity, then how do I go ahead with it? Inside the spherical cavity, how do I go ahead with it? So the way we go ahead with it is this. That what I did is first I understood okay. So here we have this. So at the center, suppose this is the center of the sphere. So I have this as one vector. I'll call this the E1 vector. I have this as another vector. I'll call this the E2 vector. I'll call this as vector. I'll call this the ER vector. From the triangle law, you can see that E1 vector plus E2 vector gives you ER vector. What is ER vector? ER vector is the resultant vector. If ER vector is the resultant vector, now E2 vector is equal to 0. Why? Because if I draw a Gaussian surface here, the net electric field there is 0. So if the net electric field there is 0, I'll see that E1 vector is equal to ER vector, meaning inside the cavity, the electric field at the center of the cavity is same as the electric field anywhere inside the cavity. Now you'll ask, what is the electric field at the center of the cavity? How do I do it? Assume the sphere was full. If the sphere was full, for this charge, I can calculate what is the cavity electric field. Now you are removing that cavity part, so E cavity. So this will be the electric field at the center of the cavity. Center. This is due to the cavity. Okay, so this is what I wanted you to communicate. Yeah, so I did a problem also today to explain to you the same thing. Okay, now some students were asking me, sir, why are you taking a spherical Gaussian surface? Look, I am not taking a spherical Gaussian surface. I take my Gaussian surface every time depending on the geometry. My Gaussian surface should actually satisfy 2 points. One, that electric field should be the same at all points on the Gaussian surface. the electric field should satisfy, the choice of the Gaussian surface should satisfy this, that electric field should be the same at all points on the Gaussian surface. Why should it be this? It should be this because, see, I have E dot dA is equal to Q by epsilon. Now, it is very difficult, if I take any orbit surface, it is very difficult to perform this integral. So, to simplify this, suppose E is the same everywhere on the Gaussian surface, E can come out of the integral because then E becomes a constant. So, if E becomes a constant, E dA becomes Q by epsilon naught. Now, it is easy for me to perform this integral. This is easy. This is very difficult. Literally impossible. I don't know so much of maths. So, suppose I have a line charge distribution like this. Suppose I have a line charge distribution like this. Then, and I want to find out what is the electric field at a distance r from here. So, I want to choose a surface such that everywhere it is r distance from the wire. So, here also it is r, here also it is r, here also it is r. Now, suppose this was the wire, I choose a spherical Gaussian surface. Here it is r, but here it is not r, here it is not r, here it is not nothing, here it is nothing. So, what will happen is that each of these points, the electric field is not the same. Now, the electric field is varying. So, I cannot bring E out of the integral. If I cannot bring E out of the integral, then it is a useless step. I mean, I can't, it's so difficult. But here, the electric field is the same. Then you will ask, sir, what about this? No problem. What is the flux through that? Because the electric field is like this. What will be the flux on this? The flux on this will be 0. So, those surfaces are of no use to me. So, I do a cylindrical Gaussian surface. And I don't do a spherical Gaussian surface. Now, suppose I have a point charge. Now, if I draw a cubical Gaussian surface, see, this distance is different, this distance is different. So, at every point here, the distance from the charge is different. So, at every point here, the electric field will be different. So, I don't do a cubical Gaussian surface because I can't do E dot dA. I can't perform this integral. Do you understand? Even if I draw a cylindrical Gaussian surface here, now I can't because this distance is different, this distance is different, this distance is different. So, even for a cylindrical surface, I can't find out. But if I have a spherical Gaussian surface, it is so easy. This is same distance from here, same distance from here, same distance from here. So, E is the same. Because E is the same, the integral E dot dA becomes easy. E integral dA. Okay. Then sometimes you may say that, okay, there might be a case. So, first thing is, I said there are two conditions. One is that E must be same. And there is a second condition. I don't want a cos here. So, I am choosing a Gaussian surface necessarily where this angle is 90 degrees. So, only where it is 90 degrees I am choosing. So, this is the wire. This is the electric field, infinite wire. So, this is the electric field. So, I am choosing a surface perpendicular. Okay. So, the angle between the Gaussian surface and the area vector should be 0, or between the electric field and this plane be 90 degrees. So if this is the area vector is perpendicular to it. So it should follow these two. This is true whenever the surface is equipotential. We will see this when we do the next chapter. When it is equipotential. Actually, this was a question in a JEE mains paper. How are you choosing the Gaussian surface? So option 1 was E is the same at all points. Option 2 was spherical. Option 2 cylindrical. Option 4 E is the same at all points and the surface must be equipotential. So D is the right answer. First one is wrong. Why should the surface be equipotential? Only when it is equipotential, this angle requirement will come. That is, there is no cos theta. So if there is no cos theta, E is the same, it becomes easy for me. So that is how I am choosing the Gaussian surface. So if there was a plane like this, I understood that the Gaussian surface, the electric field will be outside the plane on either side. So I chose an equipotential surface perpendicular to it, then equidistant from it. So I chose a cylinder. Now here you can take anything, you can take this can be anything. Why? Because the electric field is in this direction, so the flux here is 0, so I don't care. So here basically this has an area, you can take any shape now, it can be any shape. But just make sure that both the sides of shape is the same. Okay, so I hope I clarified this question on how do we choose Gaussian surface. How do we choose a Gaussian surface? Yeah, so kindly go through this and make sure that you are making your notes. I'll wait for a few minutes. This chapter takes some time to understand. This chapter takes some reading also. Okay, so don't get boggled down if it is taking too much time to understand. It takes a little time. The questions that you get, if you follow everything that I'm doing, will be you will be able to answer those questions quite easily. It won't be a big problem for you. Okay, so just try to follow, try your best. That is the most important thing. We will do this if the need is. We will do this chapter again. That is not a problem. But from your side, please try to think and then learn. Understand that there is a competition at the end that you have to fight. And only if you try from now, you will be able to fight. Okay, so this is how you go ahead with the Gaussian surface. Now, I want to ask you a question. Here is a question. Yes, I explained. Here is a question. See, this is the origin. This is the origin. This is the origin. There is a cube. The dimension of the cube is 2. This is 2, 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 2, 2, 2, 2. Everything is 2. The question is, flux 1 is the flux through the surface ABCD. Phi 1 is the flux through the surface ABCD. Phi 2 is the flux through the surface BCGF. BCGF. On this surface, the flux is, Phi 2. Phi 2. The electric field in this region is given as this 4x I cap minus y squared plus 1 j cap. This is the x-axis. This is the z-axis. This is the y-axis. The question to you is, what is phi 1 minus phi 2? What is phi 1 minus phi 2? Phi 1 is the surface here, is the flux through the surface here. Phi 2 is the flux through the surface given here. These are all cubes of dimension 2. The question, the electric field in the region is 4x I cap minus y squared plus 1 j cap. The question is, what is the flux through this? So let me try to help you find out. Now you see here, I'm looking at phi 1 first. The area vector will be vertically upwards. So what will you say the area vector is? First thing, what is the area of that? Area of that will be 4 times 2 into 2, 4. And can I say it will be 4 k cap? Can I say it will be 4 k cap? Now this vector here for this will be, this is the area vector. So that will be another 4. And what will be that vector? That vector will be I cap. So this wall here will have an area vector perpendicular to the wall. So the perpendicular to the wall is k cap. This vector here will have an area vector perpendicular to this wall. So this wall is in the YZ plane. Perpendicular to that is I cap. So it is 4 I cap. So flux 1, can I say it will be E dot A? So I have 4x I cap minus y squared plus 1 j cap dot 4 k cap. How much will it be? I cap cross k cap is 0. Now j cap cross k cap is 0. So flux through the first wall will be 0. Now let me go to the second wall. Second wall, again I have 4x I cap minus y squared plus 1 j cap dot 4 I cap. So I cap dot I cap will give me 16x. What is the x value there? X value there is 2. So 16 into 2 will give me 32. So the answer is 1 minus 32. So what is 1 minus, 0 minus 32? So 0 minus 32 will be what? Minus 32. So the flux will be minus 32, whatever SI units. Do you understand? I will wait for 2 minutes. Can you work it out? I gave you the origin. I gave you the x-axis. I gave you the z-axis. I gave you the y-axis. We have a cube there. I asked you to find out what is the flux on one face of the cube minus the flux through another face on the cube. We found out. I got this minus 32. Please work it out and see. So I hope you're able to understand how to go ahead with this. Right? Try to do this. I will explain again. I will redraw the diagram and then explain again. So I will explain again. If you have to spend some time thinking about it, I will explain again. I am not expecting you guys to get it in one go. I am expecting you to only think. That's all. E is equal to 4x I cap minus y squared plus 1 j cap. Okay. Then I do the electric. This is x-axis. This is z-axis. This is the y-axis. And we drew the cube. So this doesn't look like a cube, but okay, assume adjust. Adjust, it looks like a cube. Okay. The easy thing is to do it again. So this is the z-axis at the back. This is the y-axis. This is the x-axis. This is the x-axis, and this is the y-axis. I mean z-axis. I have told you that this cube is of dimension 2. Now I told you that flux 1 is the surface, is the flux on this surface. So how do I find it out? So flux is equal to E dot dA. Now area vector is perpendicular to this. Do you see that the area vector will be like this? So it is parallel to the z-axis. So that area vector will be k cap. Now what is this area going to be equal to? I told you it's a cube of dimension 2. So 2 into 2, 4. So surface 1 has an area vector 4 k cap. Now when I know E dot dA, it will give me 0. Because I cross k is 0, j cross k is also, I mean I dot k is 0, j dot k is also 0. So it will not give me anything. Then suppose I consider this wall. For this wall, the area vector is perpendicular to this, that is along the I direction. So when I work it out, this will also be 4. So when I work it out, it will become 16x. What is x equal to here? X is equal to, I said it's a dimension 2. So 16 into 2 will give me 32. So the answer would have been 0 minus 32 SI units. So that will be minus 32. So this is how you find out the electric flux. E dot dA. Okay. Then another doubt that was asked is this. I have a sphere. I have another sphere. I have, let's say, yet another sphere. Electric field here is, suppose I identify points A, B, C, and D. Charge on this is minus Q. Charge on this is minus 5Q. Charge on this is plus 7Q. Let there be a charge Q here on this. So the question is, what is the electric field at A, B, C, D? Now, the electric field at A is equal to, I draw a Gaussian surface at A. If I draw a Gaussian surface at A, what is the electric field? What is the charge inside? 5Q minus Q, minus 6Q minus 5Q. So minus 5KQ by R squared. What is R? R is this radius. Whatever it is this radius. So, so I can say that R is greater than RC, less than RB. Now, if this is my point, so the electric field B is equal to total charge inside Q0 minus 5Q QQ. So plus 2KQ by R square. Now, please don't think that this R and this R are the same. They are different. This R is some R which is greater than radius of the outermost, whatever it is. So it's the same symbol that has been used, but this R is a different R from that. Okay. Then EC. EC here is total charge inside is 0. So the electric field at C is 0. Not only at C, the electric field anywhere between the two, the sphere, the innermost sphere and the second sphere will be 0. Now at this distance, it is equal to KQ by R squared. Now what is this R? This R is this distance, whatever it is. Now this R is different from this R is different from this R. Each of those R's are different. Now I found out the electric field. I could have also asked you to tell me what is the charge inside and outside. So the charge here is Q. The charge here will be minus Q. The charge outside will be 0. Then the charge inside here will be 0. Charge outside is minus Q, minus 5Q. Then the charge inside here is plus 5Q. And the charge outside is 2. Why? Because everywhere there is a conductor there. If you draw a Gaussian surface, electric field is 0. So inside the conductor, the net charge must be 0. Okay, so inside the conductor, the net charge must be 0. Okay, so I hope you are able to understand these things. Yeah. Now, the other day I asked you a question. That there are 4 charges here which are placed at the corners of a square. So, above here, I place a charge, a negative charge, and push it up. When I push it up, there will be these 4 charges which will be working on that. Suppose I push it up by x. This distance from one end to the other end is root 2a. By 2 will make it a by root 2. So the force on that charge will become k, 4 times k, capital Q, minus Q by r squared. R squared is what? A by root 2 plus x the whole square. Plus the direction of this force is this side, this side, this side, this side. So I have to take the components onto this side. So the component that I have to make, I have to take will be the sine of this angle. Will be the sine of this angle. So sine of that angle will be x. Will be x. I mean this is not. I'm sorry, I'm making a mistake here. So whole square by root over of a by root 2 square plus x square sine theta. Sine theta is going to be in the downward direction. So that is the force. So now when I simplify this, I get the force is equal to 4 times k capital Q small q by this thing. I can now assume x is small. This x I can't remove. That x will remain. This I can assume x is small, and I'll get a by root 2 whole cube. I'll get a by root 2 whole cube. Now you see this is equal to m into a. So the m comes down and I get a. You see this acceleration is proportional to x. So whenever acceleration is proportional to x, I will say that the motion is simple harmonic. And what you get here is what is omega square. So this 2 root 2, this root 2 cube will become 2 root 2. So you get omega squared is equal to 8 root 2 k capital Q small q by a cube m. equal to 2 pi by omega. So that will give you 2 pi root over of a cubed m divided by 8 root 2 a capital Q small q. This is how you do it. So those of us who did not, please understand how to go ahead with it. I'm happy that many of you, more than 40-45 of you all have submitted the answer. I'm very happy for them. The others, make an effort, make an effort. We don't want right answers. Nobody wants right answers. I just want you all to work. It's like 10 days back, you were not thinking about electrostatics. Now you're thinking something about electrostatics. I'm happy. And I understand that that is the right direction. Some of you are able to do it, some of you are thinking about it, some of you are just beginning to think about it. Do not worry. Do not worry. This is the way to learn. Okay, nobody has learned anything by reading once. If by reading once some people have learned it, then the world would have been a very, very different world today. Okay. So I hope you are able to understand. Please digest this. See, I have just tried to move the charge a little up. Because it's a negative charge, they are all attractive forces, so they are being pulled. So I'm trying to find out the downward component of the force. So first I found out the force, then I took the downward component sine theta. All four charges will be equal. So I just simplified it and I got the answer. T is equal to 2 pi by omega. Okay, I repeat again, this is not an easy question. Thinking like this takes a lot of time and effort. I just want you to make a beginning. Okay. Okay, then one more area where I mean, students asked me a few questions was when I worked with the electric field and I placed a dielectric in the electric field. So let me work that question out again. So yeah, so there is a electric field. In that I placed a dielectric material. Dielectric constant K. What do you mean by dielectric constant? Dielectric constant is the electric field in vacuum by electric field in medium. That is the definition. Okay, so electric field in medium is equal to electric field in vacuum by K. So electric field here is E. So the electric field here has become E by K. This is given. This is known. Now the question, okay, now I am trying to think, okay, why did it happen? So the answer for that is because of creation of dipoles. Positives are on this side, negatives are on this side. This gives rise to a reverse field. So it is this reverse field which is weakening the electric field. So the original field minus the electric field due to polarization is equal to E by K. So the electric field due to polarization is E minus E by K. So that is E common 1 minus 1 by K. So if the dielectric constant was 5, then the electric field due to polarization was 4 times E by 5. And the final electric field inside the dielectric would have been E by 5. 4 times E by 5. And the electric field inside the dielectric would have been E by 5. Okay, are you able to understand this? So this is what I said. Then I explained to you a question. Suppose there is a charge here 4Q and there's a charge here. Okay, there's a charge here Q. There's a charge here Q. In between, for a distance D by 4, you placed a dielectric which has dielectric constant 16. The question is, what is the force between the two charges? What is the force between the two charges? See, if the dielectric would not have been there, the force is K Q squared by E squared. If you had fully filled it up with the dielectric, the force would have been K Q squared by 16 D squared. Do you understand this? Now the 16d squared, I can write it as kq squared by 4d the whole square. So if this region was fully stuffed by a dielectric, this would have been the force. That means a region having a separation d fully stuffed with dielectric has the same force as 4d in vacuum. 4d in vacuum, which means 4d in vacuum is equal to d in medium. So 1 in medium will be equal to 4 in vacuum. So d by 4 in medium will be equal to 4 times d by 4 in vacuum. So dd gets cancelled, so it will be equal to d. So now this distance, this vacuum, there is vacuum here or air here, that and this. So that is already 3d by 4. To that I am going to add d. So the net distance is 7d by 4. So now I can calculate F is equal to kq squared by 49d squared into 16. So it becomes 16 by 49 kq squared by d squared. This was the original force. So it becomes 16 by 49 times the original force. Okay, so this is how I work it. So I said first it is full air, full vacuum. Now this full vacuum is equal to 4d the whole square. Then I said d in vacuum is equal to, d in medium is equal to 4d in vacuum. So d by 4 in medium must be equal to d in vacuum. So this distance here is 3 by 4 times the distance in vacuum plus 1 by 4 times distance in medium. This 1 by 4 times distance in medium is equal to d in vacuum. So it becomes 7d by 4. Now when I substitute, I get the answer. Okay, think about it. Okay, so I will stop here. I will see again tomorrow. Message me whatever more doubts you have, we will answer. Read your textbook. It takes at least 2-3 readings for you to understand. Nobody on earth can understand it in one go. Even if we understand, many times we don't understand it right. Okay, so please read the chapter 2-3 times. That is the only way to get it. Okay, bye. Thank you. Today we had a good session. There was no disturbance by the system, by the internet. I should thank Chidambaram for that, and best wishes to you all. If you all have any doubts whatsoever, tomorrow only, previous slide once more. Sir, please repeat slide 12 once more. Okay, I will do that. Yeah, you want me to show you slide 12 once again, right? Oh, they already changed me. Just a minute. Vishnu?
Sir, just 1 minute, sir.
Yeah.
Sir, check my version.
Yes, so slide number 12 you want to show again. So here is slide number 12. You want me to explain that again? Okay, slide number 12, you want me to explain that again? I'll explain that question again. See, suppose there is a charge Q here. There is a surface here. Suppose on this the charge is minus Q. Okay. Now, because this is Q here, on the inner walls it will be minus Q. Induced charge will be minus Q. So on the outer walls it will be 0. Now there is another surface here. Another surface here. On this there is 5Q. So on the inner wall now, total charge inside must be 0. This is already 0, so it will be 0. Then on the outer wall, 5Q will come. Now, if I ask you what is the electric field here, to find out the electric field here, you just draw one Gaussian surface and find out what is the total charge inside. The total charge inside is 5Q minus Q, Q. Total is 5Q. So the electric field is 5kQ by R squared. And what is R? R is this distance from here to here. Now I can ask you what is the electric field here. So the electric field here will be K Q. Q is 0, so 0. Now I can ask you what is the electric field here. Electric field here is KQ by R square. Now this R and this R are not the same. This is a different R, this is a different R. This R is this much and that R was this much. Yeah. So that is what I have shown in slide number 12. So I asked you to find out the electric field here. So the electric field here, inside it, how much charge was there? Minus 5Q, Q and Q. So minus 5Q. So minus 5KQ by R square. What is R? R is the distance from the center to this, whatever it is. Okay. Next, I asked you electric field at B at this point. So I drew this surface here. Inside it now, how much charge is there? 7 minus 5, 2 minus 1, 1 plus 1, 2. So 2KQ by R squared. What is R now? R now is from here to here. Okay. So that is how I found out. Okay, then thank you. Let me see if there's anything else anybody wants. Slide number 12. Okay. Okay, friends, thank you so much. See you again tomorrow.